All right, so here's an example of an inductive proof. First of all, I have this problem that the textbook asked me to figure out. So they're telling me that the sum of this particular sequence, 1 plus 2 plus 2 squared plus 2 to the third plus 2 to the n minus 1 equals 2 to the n minus the whole number 1. So there's the sequence. To prove that this is true using an inductive proof, you have basically 3 steps. First, show that the first term is true, or the sum of the first term. So, S of 1 equals 1, right? The sum of the first term is just 1, because the first term is 1. And then use the formula. So use the formula for one term and see if you also get 1. So this means 2 to the 1 minus 1. 2 to the 1 is 2, so that's 2 minus 1. Well, that equals 1. So, that's true. It's true for the first term. So I proved it was true for the first term, so now I'm going to assume that it's true for the kth term. So that means that S sub k equals 1 plus 2 plus 2 squared plus 2 to the third plus 2 to the k minus 1 equals 2 to the k minus 1. So I'm assuming that that's true. So, true for all intent purposes. That statement is true. Now I'm going to show that sk plus 1 is true based on that assumption. So first I have to set up what does sk plus 1 looks like. Well, it looks just like sk, except for I go one more term. So 2 to the third plus dot 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 2 to the k minus 1 plus the k plus first term. So in place of k, I'm going to put k plus 1. So 2 to the k plus 1 minus 1 equals 2. In place of k, I'm going to put k plus 1 minus the whole number 1. So when you're doing the k plus first term, you have to go one more term after the k term. So the k term ended here, so the k plus first term is here. Now, it's pretty easy to prove this. I know the sum of the first k terms. It is defined by this. So I'm going to just use substitution. I'm going to replace this whole series now with what the sum of it is. So, sk plus 1 equals 2 to the k minus 1 plus that very next term, which is 2 to the k plus 1 minus 1. We'll do the arithmetic there. That ends up being 2 to the k. And I have to prove that that equals that. So I can't touch that side. I'm just going to prove that that is equal. So let's get the computer screen to show a little bit more roomier. So how do I prove that this side equals that? Well, let's add like terms. 2 to the k and 2 to the k. That's 2 times 2 to the k minus 1. And that equals, again, that term. So I've got to prove that this equals that. Well, can I multiply this 2 times this 2? Oh, be careful. They're the same bases, but this is 2 to some exponent. It could be 2 to the third, so maybe it's 8, or 2 to the fourth, or 2 to the fifth. So I'm just going to add my exponents. When I multiply the same bases, what do I do with my exponents? I add. So 1 plus k. So this is 2 to the 1 plus k, can be written as k plus 1 minus 1 equals. And look, I got that answer, right? 2 to the k plus 1 minus 1. So did I prove it? Oh, yeah, I did. That's how you prove it by induction, okay? I show it's true for the first term. I assume that it's true for the kth term. And then I show the k plus first term, which is the very next term. And I did it by substitution. I substituted this whole part of the series for that sum. Good luck. So remember when you're doing these that it's important. You always work this side of the problem, and then that side just stays the same. And finally I proved that this side, I could get to equal that side. All right? There you go.